Safety 21 DICE Transportation Fellow. The Smart Safety Connection series is sponsored by Safety 21 as an opportunity for faculty to showcase their current transportation projects. It's also an opportunity for students, faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster interdisciplinary collaboration. Please note that the session is being recorded. If you're on Zoom, feel free to send in your questions at any point. Same if you're in the audience, just raise your hand. And now I would like to introduce today's speaker. We have Lindsay Graff, who is a Ph.D. candidate in the Department of Civil and Environmental Engineering at Carnegie Mellon University. She holds a bachelor's in mechanical and aerospace engineering from Princeton University and a master's degree in public policy from Carnegie Mellon's Heinz College. After completing her bachelor's degree, she spent 3 years working for Delta Airlines in the revenue management department, where she forecasted passenger demand across the flight network. Her current research focuses on improving the design of urban multimodal transportation networks to facilitate access to goods and services for all population groups, working with Catherine Flanagan. She's an assistant professor in the Department of Civil and Environmental Engineering at CMU, and she also holds a courtesy appointment in the Department of Electrical and Computer Engineering. Please help me welcome Catherine as they tell us about their University Transportation Center project, optimizing mobility subsidies and multimodal transportation networks. Thank you.
Thank you, Wesley. Okay, if it wasn't clear, I'm Lindsay. Catherine is one of my advisors. She's not with us today, as advertised on the flyer. So said I will give the presentation in her place. So yeah, I am not an assistant professor. I am a PhD candidate in the civil engineering department. So today I will give a presentation titled Optimizing Mobility Subsidies in Multimodal Transportation Networks. So there are two concepts here, one of which is mobility subsidies, and the other one is multimodal transportation networks. So those two topics will guide my talk today. So that said, I'll start with the agenda. So steps 1 and 2, I want to motivate the need for multimodal network modeling, and then describe the process for designing a multimodal network model. So that was my first project. So we have since completed that work, and it is submitted for publication. What I'm now working on is this idea of mobility subsidies. So after I get through that first project, I will motivate the need for mobility subsidy program design, and then propose a formulation for the optimization of mobility subsidies in a multimodal network, and then finally show the results on a toy network. We are still, in process of this method, so we have not yet applied it to the larger Pittsburgh network. So this is my second project that I am currently working on. So we'll get started with the motivation for multimodal network modeling. So here we have 6 transportation-related headlines from the Pittsburgh area news, all talking about different things. So we see several travel modes being invoked here. We have e-scooters in the bottom left, which I think that pilot program has since concluded, but there was a point where we saw them everywhere on Pittsburgh streets. We see Pogo, the bike share mode. We see in the middle, bus rapid transit project. There's a lot of construction for that going on. And then in the bottom right, we see this idea of guaranteed basic mobility pilot offers near unlimited transit access to 50 Pittsburgh residents. So that headline will actually come back around when I motivate my second work. So we'll see who is paying attention when we get there. So what we see is that transportation generally is an issue of public policy that's receiving a significant amount of media attention. So in general, I think we're all aware that the set of available travel modes is expanding. So what we learned from the last slide is that, well, commuters are no longer constrained to using a private vehicle or public transit to get to work or other essential activities. Instead, they can use several shared modes. That includes transportation network company vehicles. Those are your Uber, Lyft vehicles. Micromobility, such as personal bike share, scooter, and then also car sharing and just classically walking. But why would you take one mode over the other? So, in general, I think we can all agree that our decision to take one mode versus another reflects cost trade-offs. So, for example, you might think, well, what is the monetary cost in terms of dollars? Many times I would love to take an Uber Lyft back from the airport, but it's expensive, so I don't. I take transit. But Transit's not necessarily often reliable. You're wondering when you decide to take PRT, well, will it come on time, and will it be too full in the winter? Sometimes you may also want to bike or take a scooter, but you may be worried about the risk of the path. So in general, for this research, we said, well, a traveler considers 5 cost considerations, those being travel time, the price, the risk, the reliability, and the discomfort. And then, each one impacts your mode choice differently. Okay, so the objective of minimizing total cost can lead to the construction of multimodal routes. So here's here we have a contrived origin-destination pair. We have Hazelwood Green in the bottom, going up to Mellon Park. So we have different cost trade-offs. So a potential multimodal route, let's say you're down here at Hazelwood Green. If you actually try to go to Mellon Park by public transit, it's not a good option. You'll have to transfer bus lines, and the whole process will take you 45 minutes on a good day. Well, what if there's a bike share station nearby? You may want to solve your first mile problem by taking a bike share, maybe biking a mile and then or a mile or two, and then getting on public transit for your final segment. Alternatively, you could take transit for the early segment and then a spin scooter for your to your final destination, or no transit at all, maybe taking something like a spin scooter to a zip car. So these are just possible multimodal routes that can be considered. But the issue is that real-time routing is typically conducted for single mode, single cost travel. So single mode being one travel mode, whether it's car or transit or biking. Single cost being just travel time, so not considering all of those other costs that I had mentioned previously. So here's the familiar Google Maps interface. So if you want to go from Hazelwood Green to Mellon Park, you have to choose which mode am I using. So here, let's say you selected the private vehicle. Well, it returns a route to you that takes 15 minutes, so it's optimized for travel time. Alternatively, you could select public transit, and it shows you what seems to be a rather inefficient route, but you are constrained by the PRT's network structure. So it triples the travel time relative to private vehicle, or you could select biking, and it also gives you a route. So moreover, previous accessibility research considers single mode, single cost, single time of day travel. So accessibility metrics aim to capture how well a city's transportation network facilitates access to important destinations. So one such metric that's very commonly used in practice, because it is quite interpretable, is called this cumulative opportunities metric. So here's a map of the Pittsburgh neighborhoods. We'll say we're just considering one neighborhood center, the Red Star. And then we have various points of interest around. So if you want to know how accessible are these points of interest, what this metric will do is you say, okay, well, you're a transportation planner. You have to set a travel time threshold, let's say 20 minutes. And then you count the number of, quote, opportunities reachable within the travel time threshold. So let's say these are jobs, these black markers are jobs, and your travel time threshold is 20 minutes. Well, then the cumulative opportunities metric of accessibility to jobs for this neighborhood center is 1, 2, 3, 4, 5, 6, 7, 8. So very, very simple metric to calculate, and like I said, for that reason, it's often used in practice. But as noted up top, this metric is often calculated just for single modes. So you want to know the cumulative opportunities metric for private vehicle travel, or the cumulative opportunities metric for transit travel. And the only thing you're going to do is set that travel time threshold. So that's your single travel cost. So that said, we want to try to evaluate accessibility in a multimodal network. So that said, our research objective is to develop a multimodal network modeling framework to measure accessibility that considers a diverse set of time-dependent travel costs and travel modes. So a lot of words there, but what we're trying to do is develop this model that considers all of these travel modes at the same time. So develop a model that allows for multimodal routes, considering, bike share, scooter, TNC, or transportation network companies. Considers these 5 travel costs: the time, price, risk, reliability, and discomfort. And then evaluates accessibility at many points in time. So oftentimes you see accessibility just measured at 8 a.m. or peak morning, or at 5 p.m. peak evening. So we want to do this at almost a continuous time. So hopefully that was properly motivated why we want to develop this model. Now I will show you how do we actually do that. So I'll start with some steps, and then I will show you some images. So steps for designing this network model. So first we build unimodal graphs for the study area. I will show those soon. And then we will connect these graphs by transfer edges to build what's called a super network. That's a routable multimodal network model. We will connect our origin destination nodes to the multimodal network, and then assign each edge in the super network total travel cost. So the point is, after we complete these four steps, we should have a multimodal network model such that you can query any origin destination pair, and you will be able to find a multimodal route that potentially traverses many travel modes and is optimized for a total travel cost that considers factors other than just travel time. So let me show you what this looks like. So here's a toy network. This is just a fake network of 8 intersection nodes. So we have I1, 2, 3, 4, 5, 6, 7, 8. Those are just street. You can think of those as street intersection nodes. And then street edges are these arrows. And then we have other, quote, important nodes in the network. Those being, like, in this green, a bike share station. In the black, a parking node. Or in the maroon, a car share station node. So these are, other nodes that we need to model. So this is our, our base case. We have a network that looks like this. And now I will show you how do we actually extract unimodal graphs from this multimodal transportation network. So let's start with the personal vehicle network. So in the personal vehicle network, you are only concerned about, your only special nodes are the parking nodes. You're going to use the regular street intersection nodes and street edges to drive, and the only special ones that you might use are the parking network nodes. You're not going to use a car share station. You're not going to use a bike share station node. So we have built out the personal vehicle network. For the car share network, you also might want to park the vehicle, but you also have these car share nodes. So what we do is we connect these car share station nodes, and we connect the parking nodes to their nearest intersection nodes. Why do we do that? Well, if you don't have a connection between the intersection and the parking, then you cannot access it on the graph. It's not what we call routable. You cannot get from point I6 to parking 1 if this network link does not exist. So that's why you have to build out these connections. And then we have the Uber Lyft, which does not have any special nodes. The transit one, I'm not going to get into that. It's a bit more complicated, the reason being that many routes use the same bus stop. And we have to be able to model it such that you can transfer between, let's say the 61A and the 28X at a given point. We have the scooter graph. The reason that those top edges are not included is because we said those edges are not bikeable. For example, they might be highway edges, and you cannot use them. And personal bike, same thing. And then bike share is very similar to the car share one. So we have our special nodes being the bike share station. And again, we build out these little connections such that you can go from the biking network to the station nodes. So that said, at this point, we have all our unimodal graph models. You can imagine them as layers. So what we're going to do is connect them by what we call transfer edges. So here is a super network model that includes some transfer edges and the origin destination connectors. I only considered 4 modes here. I didn't include all of the other modes because the Graff super network gets very messy. So I said, let's just say we're thinking about TNC, which is the Uber Lyft, transit, bike share, and then also the walking mode. So we have layer 1, layer 2, layer 3, and then we connect them at logical points. For example, the transit network is connected to the bike share network by connecting a bus stop to a bike share station, because you can only access the bike share network by transferring to a bike share station. The public transit is connected to the Uber Lyft network to the point, sorry, if you're going from the transit network to the Uber Lyft, you go to the point nearest your bus stop, because logically you would ask your driver to pick you up at the point in the Uber Lyft network that is nearest the bus stop. And then we say all of these transfer edges are traversed by walking. That's why the walking mode is invoked. So we also include our origin and destination. Those are the orange points. And we connect. So we connect, for example, the origin to all bus stops within, let's say, half a mile. Or similarly, all bike share station nodes within half a mile. And same thing with the destination. So at this point, what we have done is we have created what's called a routable network model. That means that we can start at this origin, and we can make, we can connect to any of the travel modes, travel mode unimodal graphs, and then take some path. So we built out these transfer edges logically, such that the transfer between modes makes sense. So for example, if I included the personal bike network, I would not build a transfer to the zip car, or the car share network, because you can't just put your bike on it. Those were some just practical constraints. The thing is, we can't optimize a route yet, because if you're going to optimize, you need to put a cost on every edge. Otherwise, you don't know what you're optimizing with respect to. So you could just find a route, but you don't know if it's, quote, optimal from point A to point B. So that leads to step 4, where we assign a total travel cost to each edge. So I mentioned these travel costs in a previous slide. The travel costs we consider are the monetary cost, which we measure as the fixed cost of the edge plus its operational cost. So for example, if you're in a bike share graph, you have to pay per minute of use of bike share edge. So you can look at the length of the edge and then make an estimate of how long it will take you to traverse the edge, and then find your operational cost. The average travel time, so that we'll say is the edge length divided by the average speed you're going with the mode. Unless you're in transit, then we'll just use the publicized schedule to figure out the travel time. The reliability, which we measured as the 95th percentile travel time, that's typically used as a metric of reliability. The risk we defined as the crash risk, which we were able to calculate by calibrating it using previous crash data. And then the discomfort, which we were able to look at the literature and find some survey data that asked people, what is your comfort level using these various travel modes, such that we could calibrate a discomfort index that we multiplied by the edge length. So now we have all of these attributes for each edge. So what we're going to do is add them up. So we're going to assign a weight to each one, and then add them up and get a total travel cost. So the weight of each one is interpreted as your value of the cost component. So for example, W2 here would be your value of travel time. The point of that being, well, now you can compare all of these on the same scale. So if you have value of travel time times average travel time, now you have some monetary value, which can be compared with monetary value up top. Similarly, you can have a value of reliability times reliability, and you get out a dollar amount. So now we have everything on the dollar scale, and we can add them up to get a total travel cost on each edge, such that we can appropriately optimize a route. So this is what Google Maps does, but my intuition is that they return you a route optimized for only travel time, as opposed to all of these other cost considerations. And again, only a single travel mode. So the output of Project 1 was an actual multimodal network model of a subset of Pittsburgh's transportation network. So this is my subset. You can ignore these two neighborhood names. It's just what I use for my, I just used this origin destination pair for my first project, which is why it's there. But we have the street network of this subset of Pittsburgh. And then we have the locations of all of the bus stops and bikeshare stations and carshare stations. So this should look very familiar to that small toy network I showed. That small toy network only had a few nodes. This has a lot of nodes, but we can apply the same process to build out the multimodal network. So that was the output of the first project, which is good, because now we can do all kinds of analysis. So now we will go into the second project. So I use that multimodal network model, or I will be using it to optimally design a mobility subsidy program in Pittsburgh. So what are mobility subsidies? Well, they're a monthly monetary credit provided to eligible residents to be used on a combination of travel modes. So you could think of this similar, or you could think of this as similar to SNAP benefits. So SNAP benefits, providing food assistance to residents in need. Mobility subsidies providing transportation subsidies, or sorry, transportation assistance to residents in need. So these mobility subsidies are, they're enabled by apps such as the Transit app. Many of us use that. So the Transit app allows us to pay for different modes of travel using one payment platform. So you can actually pay for a bike share directly in the Transit app the same way you could pay for a public transit pass. So that's what these are. Are they politically viable? I think it's an important question to ask before we embark along our research. Is this actually implementable? So this was an important question to me, so I started digging in. You might recall this first headline. So Pittsburgh actually did pilot a universal basic mobility program. A few cities have done so. So what Pittsburgh did is they gave unlimited access to 50 residents. So not just transit access, they also gave unlimited scooter and bike share and a monthly allocation for a zip card. Pittsburgh was not the only city. LA did a similar thing. So they gave a mobility subsidy to, I don't remember the number of residents, but it was capped at $150. So they said, here's a mobility, debit card. Use it as you wish. So every time, let's say you take a transit ride, it debits the $150. Oakland, California did a similar thing. They gave a $300 monthly credit to be used. So it looks like cities are starting to think about this problem. So that was that was our inspiration for, well, can we figure out a method to maybe optimize this a little bit? Because the problem is that something like Pittsburgh's program, I think that's unequivocally not economically sustainable. Just saying, here's unlimited access, and moreover, it only applies to 50 residents here. So we want to maybe apply to a larger number of residents and design a program that perhaps is just more sustainable in the long run and have a wider effect. So let's see, how can we formulate this? So let's talk about, well, what's the framework for this optimization problem? Okay, we'll start with our underlying assumption here is that, let's say a city has a fixed budget to be used on mobility funds for residents in need. Again, we can equate this to the SNAP benefit program. There's a fixed budget and cities must allocate accordingly. So we'll say that the program stipulates that all eligible residents are provided with a bus pass. Why? Well, preliminary results from Oakland's experiments shows that most of the rides used for their mobility subsidy program were actually taken on transit. And then I think it's widely understood that transit is the backbone of any transportation network. So then the question becomes, well, now you have a remaining budget, how should you allocate it? So once you give everyone their monthly bus pass, you might have, let's say $20,000, $50,000 remaining. What should we do with it? So here's a nice option. You could allocate a subsidy equally to each neighborhood. So here at the Pittsburgh neighborhood, you could say everyone gets $25, I don't know, a month, or $25 a day, whatever is possible. Advantage, that is probably the easiest solution to implement. Disadvantage, it's probably not the most equitable solution. Why? Well, any of us who have been down by the river know that transit is not so good there, versus many of us who might live over in Squirrel Hill and Shadyside know that the transit network is much more robust in those areas, and it's quite quick to get downtown. So our thought is that, well, if you have very robust transit, you might not need as many additional mobility credits to solve the first mile, last mile problem. So our proposal is that you can allocate the subsidy differentially based by neighborhood or other geographic level, say census tract, census block group, whatever you think is reasonable after consulting with policymakers. So in this solution, it might be, okay, well, this neighborhood, $10 because they have very good access to downtown or job centers in general. Whereas down here, less robust transit might need a $40 credit per month, per week, per day, whatever. So this probably is, I think, unequivocally a more equitable solution because it compensates for neighborhoods with poor transit options. Disadvantage being it is potentially more difficult to implement, but that has not stopped us before, so we're going to try it. And I will propose a method, and then hopefully at a later date, consult with our stakeholders and policymakers about actually how to implement this properly. So here's a quick primer, just a quick primer on mathematical optimization problems. What these look like is you say you're going to minimize some function, f of x, over all values of x. So you're going to choose this value of x that minimizes your function, f of x, subject to some constraints. So again, this is your decision. This is what we're going to decide. We're going to choose x to minimize or maximize, in our case, an objective function, f, subject to some constraints that you have to abide by. So when I actually explain our program design, I'm going to skip the equations, but I just want you to know that this is what is actually going on. So I will just explain conceptually how do we define our objective, our decision, and our constraints in the context of this problem. So our decision is the monthly subsidy allowance per neighborhood or other geographic level. So we'll say if a person takes n work trips per month, this can be thought of as a single work trip subsidy. Example, so let's say we decide residents of this neighborhood should be allocated $100 monthly. We have 20 monthly work trips. It turns out to be a $5 per trip subsidy on average. The objective is that we want to maximize job accessibility across all neighborhoods. So where job accessibility on the neighborhood level is measured by the cumulative opportunities metric, which I described in a previous slide. I will return to that in a second. So this is what we're trying to do. We want to allocate a mobility subsidy such that we improve access to jobs for residents across all neighborhoods in Pittsburgh who need some transportation assistance. Okay, so how do we do this? How do we calculate job accessibility by the cumulative opportunities metric? Well, we have this familiar picture. Hopefully it's familiar. So we have Pittsburgh neighborhoods. We have, let's just consider one neighborhood right now, the red star. And then all of these jobs denoted by these black markers. What we're going to do is we're going to set a travel time threshold can be determined by policymakers, stakeholders, 20 minutes, 30 minutes, whatever is decided to be reasonable. And then you're going to count the number of opportunities, jobs in this case, reachable by any mode combination within the travel time threshold and the mobility subsidy value. So, for example, we might say this neighborhood can access, 1, 2, 3, 4 jobs by transit within 20 minutes. Well, what if they were to receive a subsidy, a $5 per day per trip mobility subsidy? Well, now it turns out they can access an additional 1, 2, 3, 4, 5 jobs because they can use a bike share, perhaps, to solve the last mile problem. So this is how we connect the objective function to the decision variable. So with a greater mobility subsidy, this blue contour expands outward to the gray contour. So you can achieve greater accessibility to jobs. Okay, and then some constraints. So we have a fairness constraint. So this is part of the motivation. So we want to ensure that all neighborhoods can reach a similar number of jobs by any mode combination. So let's say we're considering neighborhood 1. We have jobs reachable on the y-axis, and then the mode type on the x-axis. So the neighborhood 1 has pretty good transit access. They can reach a good number of jobs. And then we give them some mobility subsidy, and they can reach an additional number of jobs by bike share or by some combination of transit bike share, such that we have a total number of jobs reachable. Then we have a second neighborhood with poorer transit coverage, so they might need a larger mobility subsidy, such that they can reach a similar number of jobs. So what this constraint effectively does is it forces higher allowances for neighborhoods with poor transit. And then we have a classical program budget constraint. So that says that the monthly allowance, when we aggregate it over eligible residents and neighborhoods, cannot exceed the program budget. So those are, so now we've hit the 3 components. We have our decision, our objective, and our constraints. I will now, very briefly, I'm just going to flash over this. I don't even want you to look at it. But the point of this slide, that I will flash in a second, is just to show that we have to implement all of those words in equations, and then we will put the equations into some solver, and then it will return us an optimal solution. So real quick, so we have minimize accessibility weighted by population, then decisions and constraints, and then we have all of our parameters defined. Okay, that's great. So that's what I did. I took those equations, I wrote them into some Python solver, or there are other packages you could use, and then I got some results. So I tested this on a toy network. I'm in process of converting it from my little toy network to actual Pittsburgh, but I wanted to see if this could actually work on something small and interpretable. So I made this network. It's 4x4. I said, here are some neighborhoods. So each dot or node is a neighborhood that doubles as a job center, and I have the population of each one and the number of jobs available. And then I have, their connections. So I just simulated the travel time and the monetary cost by travel mode between each neighborhood and each job center. I just made it up using some reasonable intuition. And then I assigned neighborhoods 1, 7, and 13, these ones in red, as bad transit. So what does that mean? Well, since I simulated the data, the travel time between neighborhoods and jobs by travel modes, I simply added some travel time value to all transit paths originating from these neighborhoods. Because I wanted to see if this is implemented properly, then the idea is that neighborhoods 1, 7, and 13 should have a greater mobility credit. So that's what should happen. Turns out it did happen. So what do we have here? Well, on the x-axis, we have neighborhood number. And then the y-axis, the jobs reachable. So this is the objective. The objective is the number of jobs reachable and the optimal solution. So what we see is that, so in blue, you have the jobs reachable by transit. So recall that in this program design, everybody was allocated a transit pass. The problem is the number of jobs reachable by transit for 1, 7, and 13, 0, because the cumulative opportunities metric requires you to set a travel time threshold. So you can't actually reach any jobs within the travel time threshold originating from these neighborhoods 1, 7, and 13. But what we see is that they were assigned a mobility credit such that they can now access a lot of jobs using other modes. So that's the orange line. For example, we have, let's say, I don't know, neighborhood 5, pretty good transit access, also received a small mobility credit such that their number of jobs reachable increases even a bit. Notice they are not, despite this constraint, the constraint I had of fairness, there's still some discrepancy. It's because, if I wanted to set the constraint such that they all must reach the exact same number of jobs, I could do that. The problem is, the problem would become infeasible. It's not possible to solve because of the underlying network structure. Some places, like neighborhoods 5, 6, 10, and 19, they exist in a good spot in the network, and they have good transit coverage, so they can simply get to more places. Okay. And then finally, we have the optimal solution of our decision, which was the mobility subsidy. And we see neighborhoods 9 and 10 actually not even provided a mobility subsidy. They're at very good spots in the network, good transit coverage, and they don't actually need additional credit. Notice neighborhood 0 and 15, despite not being assigned bad transit, still have a pretty high mobility subsidy. The intuition there is that they exist in the corners, so they don't have robust job access. They can't, whereas 5 can go kind of anywhere nearby. 0 is a bit constrained. There are no jobs over here. So they need more of a subsidy to reach additional places in the network. So ultimately, this gives us a sense for the gaps in the transportation network infrastructure, which can ultimately inform future network investments, which I hope to do in another project. So next steps, expanding the set of possible mode combinations. I want to include all the modes in this multimodal network model. Extending the methodology to a real transportation network. So again, that's what I'm currently working on. And then consider accessibility to other services. So this model, the objective was just to maximize accessibility to jobs. That's typically used, jobs is typically used when evaluating a transportation network's accessibility. But it would also be useful to also consider other services such as healthcare or schools or parks, anything that would make a city function well. So that said, I will conclude my presentation, hopefully right on time. I would be happy to take any questions. Yeah. Oh, yeah.
Yeah, I was wondering, like it's time and cost to get to your job. And a lot of jobs for service people exist in the suburbs. And I know from experience, there are people who travel from downtown Pittsburgh out to the suburbs, which could take up to an hour to get to work.
Yeah.
And then I assume that to get to downtown Pittsburgh, they're coming from someplace else in Pittsburgh to catch the bus out to the suburbs.
Okay.
So what I'm wondering is, do you look at the wage differential between what they pay in the suburbs versus what they pay in the city to make it worth their time and effort to go out there and travel maybe an hour and 15 minutes, maybe an hour and a half to get to and back again?
Yeah, I see. So our intention there, so here in this toy network, I have just the number of jobs equal to 10, number of jobs equal to 40. So what I intend to do there is to look not just look at the strict number of jobs, but look at the type of jobs and weight them accordingly by wage.
But nothing's been done yet about that. I'm just curious, because I see people on the bus who travel an hour to get out there to their work, and I'm wondering, are they getting paid enough to make it worth their time to travel? I guess if they take the job, it must be, but, you know, if the employers out there have to pay more to get people to come that far in that amount of time.
Wait, so then what are you asking?
Well, I just wonder if anybody's looked at that.
Oh, if anyone's looked at it. I'm not aware. I know there's, I've seen, actually one of Sean's other students has, developed a method to evaluate accessibility specifically to what are called opportunity jobs. Opportunity jobs being those that pay above the median level wage and do not require a college level degree. So there's that's what I've seen with respect to that question. Okay, yes, Kaya.
Yeah, I have a question. So, is there any previous research or kind of understanding about how are those microtransit options being actually used as those first mile, last mile, which kind of is we could look at, for example, the Poco bikes, but how much percent of the trips are actually people using this as a way to get to the public transit or get to their house, or it's just people who for example, us students, we just bike to school every day, that's just how we live, but it's not actually for increasing the the connections to.
Right. I have seen work that aims to classify the trip type to that purpose. I am not sure. When Pogo goes to put their bike share stations in different places, I am not sure what their criteria is. So to that point, I think it would be an interesting research project to look at how can you exactly coordinate station location or scooter dock location with transit. I hope that will be my final research project to address that specific question. Because if the stations are just where students live and not well coordinated with transit, then yes, students will use them for fun little trips instead of workers actually using them to potentially get to work. So if the network is not well coordinated, then these services will not be integrated properly with transit, which would be which I think is the ultimate vision of a multimodal transportation network. Yes, Rachel.
I have a question. For this second part of the mobility subsidy, is there any thought that you guys are putting into if a person is physically able to bike? So once you add in the multimodal component, someone may physically not be able to use a part of that network.
Correct. Yes, that's a good point that I brushed over. So yes, we can do that. So the same way that our decision is the mobility subsidy by neighborhood. You could also do it mobility subsidy by neighborhood, by population group, such that perhaps one population group, maybe disabled elderly, can use only transit and Uber Lyft. So that would, I think that would be a proper way to address that question. Yes, yeah.
I have a similar question,
Yeah.
but it's more about time of year and weather. So could we
Yeah.
distribute subsidies differently in the winter and summer when people could?
Yeah. Yes, you could. So what you would have to do is change the cost, change the travel cost, because now remember I have discomfort as a travel cost. That was intended to incorporate or encapsulate factors such as weather or biking or something, biking uphill, or reliability, when the bus comes but doesn't pick you up and just passes you. So we would have to change the travel cost and then run it again, which you could do. Yep.
More of a clarifying question, but would these subsidies be applied by neighborhood or by the individual and what their costs are?
Yeah. I think individual would get, I think the best we could do for individual is what Rachel had mentioned, by kind of population group, which modes are you physically able to use? As opposed, I think individual preference would start to get really messy. Maybe it's possible. It would be possible in this model, you know, instead of by neighborhood, you could just actually, you know, optimize over 1,000 people, you know, instead of over 10 neighborhoods. I did not do that because I'm not sure how well that could be implemented.
Thank you.
Yeah. Yes, Chris.
Yeah. Going back to your comment on feasibility.
Yeah.
It seems to be that you look at this slide and yet this would be infeasible. That the neighborhoods who are not getting subsidies would be up in arms.
Yep.
And
Yep.
you'd be subject to all sorts of legal challenges.
Yep. Yeah. I don't know yet how I will address the political fallout from this method. I think nobody has done this type of work before, so our stance is, well, let's try to get something out there, you know. Let's propose a method that other people can layer onto, and then the politicians can have their say. Yeah. Yes.
Well, let me suggest a practical
Yes, go ahead.
place that you can take a look at this.
Okay.
And that's the universities around here.
Yeah.
Carnegie Mellon basically gives everybody a transit pass for using transit. And in addition, provides a shuttle service for some neighborhoods, but not all neighborhoods.
I see.
And the question is whether that's a reasonable strategy or not.
I see. Yeah. Okay, I will look. Thank you.
I was gonna ask something around that. When you calculate your index, I mean, for us, the cost it doesn't apply because it's already included in our tuition. So I don't know how that,
Sorry, which index?
the index you calculated before,
The discomfort?
the one that includes the discomfort and the cost of the transit cost.
Okay, so the total cost of travel. Yes. Okay.
But for example, for us, it's already included in our tuition, and then
Oh, so you don't perceive the cost.
well, we perceive it, but via our tuition.
Right.
And then I don't know if it's our discomfort. I don't know if you evaluated that based on an average of cultural discomfort, or how you evaluate the discomfort in transit, or how you wage that that index.
Yeah. That was really hard. That was really hard to do. My intuition was that we should include some sort of discomfort attribute. It took me a while to kind of, get something reasonable. Again, I found some literature, that was, some survey data. To your point, I'm not sure if it was the best way to do it. You could remove the cost altogether, but let's see. The benefit of these W parameters, these weighting parameters, is that it allows an individual or a group to assign how much you care about it. So if you really do not want to be, biking in the winter or going uphill, or sure, you could send this arbitrarily high, such that you would never have to take those segments. So that's the benefit of one of the benefits why you assign this weighting scheme. Yeah. Okay. And actually, similarly, when you said when you talked about the cost, you said students don't necessarily perceive transit. So if you're a student, you could potentially assign the monetary cost to each public transit edge as 0 because you don't perceive. This model is very generalizable in the sense that an individual can tailor it to their own preferences per this weighting scheme. Okay. Oh, sorry, last question.
One more question.
Yeah.
Are there any there a way to quantify or consider the friction that might exist between different modes? For example,
Consider that friction that might exist, you said?
that might exist between like different nodes or,
Oh, yes.
or
Wait,
modes
nodes.
of transportation. For example, like a pogo bike station might not be next to a bus stop. It might be like 2 blocks away, and you have to walk
Yep.
through like a narrow sidewalk or something like that. Is there a way to factor that in?
Yeah, so that's like embedded in the transfer edge. So this bike share station is not connected to this transit stop because they're too far. Let's say they're a mile away. So the model will not allow you to make this transfer. It is connected to this one. The cost of the edge being how far are they? So that's how we account for the friction between these two modes. If it's half a mile, well, that's more friction than a block. Okay.
Well, thank you everyone for coming and thank you for sharing your work. Let's give another round of applause. A recording of today's lecture and the slides will be posted on the What's Happening page of the Safety 21 website. And if you're interested in getting more involved with transportation at CMU as a student, you can join the Transportation Club on Target Connect. And this is our last seminar of the semester, so keep an eye out in your emails for our next series in the spring. Thank you.